Okay. All right. We'll start from the beginning. So the topic before sampling distribution is probability distributions. So in that topic, we talked about probability distributions. We talked about random variables and their associated probabilities. We talked about the discrete probability distributions, that is the binomial, Poisson, and for the continuous probability distributions, they included and the normal, exponential, and uniform distributions. So that was on probability distributions. Now, sampling distributions just talks more about now as sampling. Okay, so with sampling, we can have sampling with replacement or sampling without replacement. So I think those are just self-explanatory. Okay, so actually sampling distributions is the topic that begins inferential statistics. What we have done so far was under descriptive statistics. Inferential is about drawing conclusions and making decisions based on the sample. We already know the difference between a population and a sample at this point, right? So there are reasons of obtaining a sample other than using the population, because we're saying that taking a sample or using a sample is less time consuming and less costly. The goodness with the sample is that you can still make a decision about a population based on a sample. We said earlier, I think in the opening topic, okay, there's some noise in the background. Okay, so okay, let me just mute Mole's mic. Yeah. So when you want to know whether there's salt again in the relish, you just get a small portion and test it. And based on that portion, you can be accurate that the relish either doesn't or has salt. So actually from a sample, we can obtain accurate statistics about a population. So that is why we sometimes use samples to test some parameters about the population. So in random sampling, there's what we call random sampling. And in this sampling, every object has an equal chance of being selected, and the objects are selected independently. Okay. Okay, so that's just about samples. So talked about inferential statistics. In drawing conclusions about the population or concerning a population, we can either use estimation or hypothesis testing. In estimation, we construct confidence intervals, okay? And hypothesis also just uses some evidence to test a claim about a population. So that's just a description. Okay, so a sampling distribution is a distribution of all possible values of a statistic for a given sample selected from a population. So it's a distribution of all possible values of a statistic. What is a statistic? A statistic. What is a statistic? Yes, a statistic. I'm waiting.
Oh, it's a question?
Yes.
Oh,
What a statistic
it's statistic is like a piece of data that you obtain from a study.
Again? Come again?
The piece of data that you obtain from a study.
Okay. So a statistic is just a measure of a characteristic of a sample. So any characteristic of a sample that you measure, any characteristic that you measure using a sample is called a statistic. Okay. And any characteristic that you measure using the population is known as a parameter. Okay, so that was just a quick definition. So the sampling distribution is the distribution of all possible outcomes, possible values of a statistic for a given sample size. So we have sampling distributions of sample means, and sampling distributions of sample proportions, and sampling distributions of sample variance. So after this lecture, you should be able to go back and answer question 1 of the mid assignment, because this lecture, all the questions in question 1 were based on sampling distributions. So what we are typically, or what we are just saying on sampling distribution is this. I have an example just to see how we can develop a sampling distribution. So if we have a population, okay, of 4 individuals, and we say we define a random variable x to be the age of those individuals, and we let the ages be 18, 20, 22, and 24. Okay, so we are letting x to be the age of the 4 individuals, and we have let them to be 18, 20, 22, 24. Now, suppose we want to take a sample, or maybe before we take the sample, let's find the mean. So we're just going to take an average, right? 18 plus 20 plus 22 plus 24. Divide by 4. We have 21, right? Someone is saying that there's no volume. Can you get what I'm saying now? From the group, from the WhatsApp group? Can you get me? Okay, so can you get what? Okay, so can you get what? Okay, so, all right. So I'm getting a response that you can get what I'm saying. Okay, so the average, which is the mean of the population is denoted by mu. So sometimes I just say mu to mean the mean of the population, which is that Greek symbol there or letter, mu. So the mean, the population mean is just the average, which is 21. And the standard deviation, we get it from using that formula, xi minus mu over n. Okay, so I hope we'll be able to get that value.
Madam,
No.
could you say that again?
Pardon?
Could you explain the last? Could you just say the last formula?
Okay, so the formula here we are getting the population standard deviation, which is sigma. That is the sigma letter. So sigma, which is the population standard deviation, is the square root of the summation of the xi minus mu. Xi in this case is the random variable, each random variable. So we get 18, subtract the mean, which is 21. The answer, you square it, plus 20 minus 21, square the answer, plus 22 minus 21, square the answer, plus 24 minus 21, square the answer. Then we have done the summation. Once we do that sum, we divide by n, and our n in this case is 4. After dividing, we're going to square root the answer. We should find a 2.236. Now we have 4 values for our random variable, which all have just one chance, just appear once. So that means the probability of each is just 1 over 4, 1 over 4, and yeah, all of them will have 1 over 4, which is a 0.25. So this graph just shows each random variable and its probability. Each random variable and its probability. Now, from the probability distributions, you'll see that, okay, kindly excuse me for just a moment. Apologies for that. Okay, so the graph that shows the random variables and the probability, we notice that all the probabilities are the same. So this is a uniform distribution from our previous lecture. So we have seen the mean of the population is 21 and the standard deviation of the population is 2.236. Okay, so now, suppose we want to take a sample of size 2. Like we want to pick 2 persons at a time from the 4 individuals that we have. Then what combinations do we have? We can have 18. So notice that we are sampling with replacement. We can pick one who is 18, and in the next 10, pick the same person who is 18. We can pick one person who is 18, and in the next 10 or pick one who is 20. So we can have 18 and 22, 18 and 24. So this just shows us the combinations that we have. We can pick one who is 20 and another who is 18, 20 and 20, 20 and 22, 20 and 24. We can have a sample in which one is 22 and another is 18, one is 22 and another is 20, both of them are 22. Like we picked the one who is 22, and in the second 10, we picked the same person who is 22. Okay, we can have 22 and 24. We can have 24 and 18, 24, 20, 24, 22, 24, 24. So these are all possible outcomes that we can pick if we want to pick a sample of size 2. Now we have 16 possible samples. Okay, so for us to find the mean of all these 16, it's very difficult because we have 2 values in each option. Okay, so would rather take the mean. Would say let's take the mean of each option that we have. Okay, so for the first option that we have, we say the mean of 18 and 18. We have 18. So we're going to take the mean of 18 and 20. That is just 18 plus 20 divided by 2. We have a 19. Then 18 plus 22 divided by 2, we have 20. 18 plus 24 divided by 2, we have 21. So when you take all these averages, you obtain this summary box. What we have inside here are means, okay? They're sample means of the samples that we took. So these are sample means. So we have 16 sample means. But what do you notice about these sample means? Are they the same? The values that we have there, are they the same?
No, they are not.
They're not. So since they are not equal, we can as well find the mean of the sample means. Note that we're dealing with sample means, okay, because we found some averages of these means samples that we created. So we can calculate the mean of the sample means. And because they are different, we can as well calculate the standard deviation. We want to know how these values differ from one another. So we can calculate the standard deviation of the sample means. Okay, so all of our calculations now will be based on sample means. So let's find the mean of the sample means. Okay, maybe just a graph to show the probabilities. 18, we see that how many? We just have 1 out of 16. The probability, 1 out of 16. That's a 0.06. Okay, so this graph just shows us the probabilities of each sample mean that we have obtained. Now we're going to find the mean of the sample means. So we're going to add all the 16 values. So say 18 plus 18 plus 20 plus 21 plus 19 plus 20 plus 21 plus 22 plus 20, all of them up to 24. Then we divide by 16. We're just finding the average. Can we do that? So when you do that, we're going to find that our mean is actually 21. Okay, so the standard, yes? Okay, the standard deviation now is obtained by subtracting the mean from each from each sample mean. Okay, and then the answer is squared. So you sum that for all the sample means and you divide by your n. N is still 16. After that, you square root. We're going to find that the mean of the standard deviation of the sample means is 1.58. Okay, so now we're going to compare the mean of the sample means and the population mean. What do we notice about the mean of the sample means and the population mean?
You are now unmuted.
They're the same.
They're the same, right?
Yes.
Okay, so we notice that the mean of the sample means and the population mean are the same. So in the mid-semester assignment, question 1A, you were given the population mean to be 100. Then in question A, I asked you to find the mean of the sample. The mean of the sample means. So your answer was just supposed to be the mean of the sampling distribution is just equal to the population mean, which is equal to 100. That's all. It was actually just lying in the question. So you have to keep in mind that the mean of the sampling distribution or the mean of the sample means is equal to the population mean. Are we together?
You are now unmuted.
Yes, madam.
Okay. All right. Now, what do we notice about the standard deviation of the population and standard deviation of the sample means? Are they the same?
They are different.
So it is not the same for the mean, the standard deviation. However, if you say sigma divided by root of n, sigma, where sigma is your population standard deviation, which is 2.236, and you divide by square root of n, and your n in this case is the sample size, which is 2. So 2.236 divided by root of n, you're going to find 1.58, which is equal to the standard deviation for the sample means, right? So actually, to find the standard deviation of the sample means, we just divide the population standard deviation by square root of n. Okay, so we'll see that. Okay, so the mean is just the same. I think we've talked about that. Okay, so the standard deviation of sample means is equal to population standard deviation divided by square root of n. This is known as the standard error of the mean. So the standard deviation of sample means is also known as the standard error of the mean. Now, again, in the mid-semester assignment, I asked you to find the standard deviation of the sample means. So in that case, you were just supposed to get the standard deviation and divide it by square root of n. So have we seen and noticed that the mid-semester solutions have been posted on the portal?
Yes, we've seen that.
So you have the solutions at the moment.
Yes, we do.
Okay, yeah. So I asked you to find the standard deviation. So in that case, you're just supposed to get the standard error and the standard deviation of the population and divide it by square root of n. Okay. So the population mean is equal to the mean of the sample means. Okay, so there are times when the samples are not independent. Mostly, this formula, you use it when the population size is known. So if the population size is known, and of course you know your sample size, this is the formula you use to find the standard error of the mean. Okay. But if you don't know, if your population size has not been given, then you use the formula on the previous slide. I think that's just a summary. Now, whenever we want to find the probability, we need to know the distribution of the population. And I think that is one thing that we stressed when we're talking about probability distributions. You can't just find the probability of a random variable when you don't know the distribution of the population from where the sample is coming from. So for us to find the probability, we need to know the distribution of the population we are dealing with. Now, if the population is normal, then we say that even the sampling distribution is normally distributed. So if the sampling distribution is normally distributed, then we're going to use the Z table to find the probabilities. Yeah, so that is our formula. So we standardize any value to a Z value. But when we do so, we're going to divide by the standard error. Note the denominator there is the standard error. Okay. So we know how to read the Z table or the normal table. So we'll talk about biasness in the next lecture. Okay, so if the population is not normal, we use the central limit theorem. The central limit theorem just states that if our sample size is large enough, then the population will be normally distributed. If the sample size is large enough, then the population will be normally distributed. Okay, so someone is saying that they're having disruptions of sound, losing sound and picture. Is anyone else also having this challenge?
You are now unmuted.
Just a bit. All the slides are the ones that are lagging a lot.
Okay. Okay, but otherwise you can get what I'm saying, I think.
You are now unmuted.
Okay, some people typing.
Mrs. Mond, as we're waiting for the one who's typing,
Yeah.
I see the session is being recorded. Are you going to make the recording available?
Yes, I think in the earlier. Oh, sorry. I think I was talking to. I wanted to give a response in regarding the distance students. Okay, so it's being recorded. So I'm going to download, but actually you can watch the presentation even tomorrow. So you can watch the presentation, the recording with the slides. But when I download, it will just be a recording without the slides. So I'll download that and give you the link to my Google Drive because the videos are mostly big, so they are difficult to upload on WhatsApp. It takes a lot of time. So I'll download and give you a link. But you can watch the video will also be available on Moodle for a week before it's deleted.
Okay.
Mm-hmm. All right. So that is with okay, yeah. So we're talking. Yes, we're going to share the video. Yeah. Okay, so we're talking about if the population is not normally distributed, then we use the central limit theorem. And the central limit theorem just says that if the population is large enough, if the sample size is large enough, then the population is approximately normally distributed. So we then ask a question. Okay, so it's now we have to define the definition of large enough because large enough is different from one person to another. So the definition for large enough is actually greater or equal to 30. So if the sample size is greater or equal to 30, then the population, then the sampling distribution will be normal. And then for normal distributions, we'll use the Z or the standard normal table. We have an example. Suppose a large population has a mean of, so this is mu, that means it's a population mean. A population mean of 8 and a standard deviation of 3. Suppose the random sample is 36. What is the probability that the sample mean is between 7.8 and 8.2? Okay, so before we come to the probability, I'll first ask what is the mean? What is the sample mean in this case? What is the sample mean? or the mean of the sampling distribution in that example?
Same as the population mean.
Okay, which is 8, right?
Yes.
Okay. And what is the standard deviation of the sampling distribution going to be? The standard deviation?
3.
Remember, the standard deviation of the sampling distribution is not the same as the standard deviation of the population. I gave you a formula. Standard deviation of the sampling distribution is also known as the standard error. So that's what I'm looking for. The standard error, okay, so the standard error is 0.5. Okay, now we come to the probability. So we were told that from the question, are we given the distribution? No, we are not, right? But we're just told that it's a large population, okay? So we're not given a distribution. So if we are not given the distribution, we then look at our n. Is it greater or equal to 30? Yes. Then we use the central limit theorem. What does it say? State? It states that if our sample size is greater or equal to 30, then our sampling distribution is approximately normal. So that means our sampling distribution is normally distributed. Now that we've established the fact that our sampling distribution is normally distributed, then to find the probability, we are going to use the standard norm. Okay, so that means we're using the standard norm. So to use the standard norm, we have to find the Z values. We have to find the Z values for 7.8 and 8.2. So what are those Z values?
Oh, I'm in class. Online class. Online.
Okay. So what are the Z values for 7.8 and 8.2? So when we use our formula, when we're checking, when we're finding the Z value for 7.8, it means that our X bar is 7.8. Our mean we have already established, and our standard deviation, the standard deviation of sample means, which is also the standard error of the mean, is 0.5. So let's calculate that. For 7.8, what is the Z value?
Minus 0.4. 0.4 negative 0.4.
Okay. And then the other one, okay. And then for 8.2, what are we finding? Mm. Okay, so we have 0.4 as well. Okay, so now we look for the probability. So now we have Z values. So we are looking for the probability that Z is between minus 0.4 and plus 0.4. Okay, so I hope we have our tables, our normal tables. We do? Okay, so you guys, how are you finding the 0.4? Because here there's a 0.5. 7.8 minus 8 divided by 0.5. This is 0.4. Okay. 1.8 minus. Okay, so we'll stick to the 0.4. So now we're looking for the probability that Z is between minus 0.4 and 0.4. So do we have our tables? Do we have our tables? Okay, let me just share the table. Okay, so we have our table there. We're looking for the probability that Z is between 0.4 and minus 0.4 and 0.4. So how do we get that probability from the table? What's the answer? Okay, so how do we get that answer? We know how to read the normal table. We spend a lot of time in class reading the normal table. So let's get the answers. I've shared the normal table with you. Yes, do we have an answer? Or we're still calculating? Yes. Okay, someone was typing. Okay, so there's some people typing. Zero 0.5160. Okay, we have an answer there. What do others think? Or what are others getting? The question is to find the probability. Okay, so the question is to find the probability that Z is between minus 0.4 and 0.4. 0.6, 0.67. How did you find that? So, Miriam, how did you find the 0.667? Can you guys get me or?
Hi. So
Hi.
I thought it was 0.04 and 0.4. I didn't hear the negative. I made a mistake. Let me
Okay,
calculate
okay.
again.
Okay, that's okay. Okay, Victor, okay, you guys can. Okay, sorry about that. I just muted my mic. Okay, so that is our question. Probability that Z is between minus 0.4 and 0.4. Okay, I'm waiting for answers. We labored to know how to read the table. So now you are experts. I'm just waiting for answers. Okay, I'm waiting for answers. Zero point 655. 0.6554. Okay, so I need an explanation. Okay, 0.6554 is trending now. Any explanation? Okay, now we're taking too much time, you guys. You know that we have a lot of topics. I'm asking you questions because we already know how to read the normal table. So I need to know where you're not understanding the concept. Okay, we're waiting for more answers. So far, we just have 3 answers. Okay, so 0.6554 falls under 0.4. You guys, you need to go and practice this because at this point, no one has given me a correct answer. And this is what we labored to do. Okay, so let's go through it and you need to concentrate.
You are now unmuted.
So, is that an answer coming?
Found the final answer to be 0.3108.
Okay, kindly explain to us, please.
Okay, so
That is the correct answer.
took this z value, which is 0.6554. Yes, and subtracted it with the other z value, which is also 0.6554. But from the previous explanation, you told us since it's on the opposite side, so you subtract with 1 minus the value that you have. So in this case, we have 0.6554. So that's 1 minus 0.6554. And on that end, we get 0.3446. And on the other end, we still have 0.6554, which will subtract from 0.3445, and we'll find 0.3108.
Okay. Okay, so that is the explanation. Because okay, let me just mute. Okay, yes. We are looking for the value between 0.4 and say a minus 0.4. So somewhere here we have a line and there. So we have to find the probability of everything less than 0.4 and subtract this other probability of everything less than minus 0.4. Okay. And because our table reads all the probability to the left, for 0.04, we find that this is around there. This is the probability that the table is reading, 0.6554. It is the shaded region from there, from 0.4 to the left. Okay, and this value, again, the probability to the left of minus 0.4. It is just gotten by subtracting 1 from 0.6554. So when you subtract 1 from 0.614, you subtract 0.6554 from 1, you get that value, which is this probability. Okay, so now you subtract your answer from 0.6544 and find the final answer. But you can as well just use the fact that the areas from 0 to 0.4 is the same as the area from 0 to minus 0.4. So from 0 to 0.4, we know that actually on the table, you get this probability to the left of 0.4. But we know the probability from 0 to the rest, hey, the probability from 0 to the left is 0.5. So we just subtract this 0.6554. We subtract 0.5 from 0.6554, then we get the distance from 0 to 0.4. Since the same distance from 0 to 0.4 is the same as from 0 to minus 0.4, you just get your answer and multiply by 2. I hope that made sense. So,
Madam, could you say that again, the last part?
Okay, so the probability to the left of 0.4 is 0.6554. Okay. And then you know that the probability from 0 up to the left is 0.5, right? Because this is uniform, it's divided in halves, and total probability is 1. So we have 0.5 on one half and 0.5 on another half as a probability. So we subtract 0.5 from 0.6554. When we do that, we're going to find a 0.1554. That means that is the distance from 0 to 0.4. So since the normal curve is symmetrical, it is still the same distance from 0 to minus 0.4. So your answer, you just multiply it by 2. So you will get 0.3108, which is the final answer. Yeah. So I hope you got that. So now we'll end our screen and we'll go back to our slides. Okay, so in that case, they had 0.5. So if you check 0.5, you still find that probability. Okay, so this is what we're supposed to do for question 1B, to find the probability in the mid assignment, to find the probability. So we'll do with that acceptance interval when we talk about sampling. When we talk about confidence intervals. So for proportions, when we have sampling distributions for sample proportions, we now use a particular proportion that we've been given. Okay, we have to remember that proportions, for proportion, a proportion is just the number of items in the sample having the characteristic of interest over the sample size. So proportions will range from 0 to 1. So for the distribution of the proportion, we're told that if our n multiplied by p multiplied by 1 minus p is greater than 5, then our proportions will follow a normal distribution. Okay, so so we're told that proportions actually follow a. Oh, so just a moment. Okay, so we're back. So we're told that proportions follow a binomial distribution, but if n multiplied by p multiplied by 1 minus p is greater than 5, then we can approximate the proportions using the normal distribution. So it is very important whenever we're talking about proportions to first check whether that condition is satisfied. If it is, then we can go ahead and use the normal distribution. Now the mean or the expected value of the sample proportion is equal to the population proportion. And the standard deviation of the sample proportion, the variance, is just equal to P, which is the population proportion, multiplied by 1 minus P divided by N. So that is the variance. So the standard deviation, you just square root the variance. Okay, so that is how we standardize the proportions, that is obtaining Z values for proportions. So that is the formula. Okay, we have a question. If the true proportion of voters who support okay, the slides. Okay, so that's our example. If the true proportion of voters who support proposition A is 0.4. What is the probability that a sample space, a sample of size 200 yields a sample proportion between 0.4 and 0.45? So that's our question. We first check, for us to find the probability, we need to know the distribution of the population. Okay, so we first have to know the distribution. So to find the distribution, we first check if the proportions can be approximated by the normal distribution. So we first check n multiplied by p multiplied by 1 minus p. Our p is 0.4. Our n is 200. 1 minus p is 0.6. Okay, so let's check n multiplied by p multiplied by 1 minus p. What does it give us? Okay, let's check that formula. N multiplied by p multiplied by 1 minus p. What is it giving us? Our n is 200, our p is 0.4. Okay. So I'll mention the page numbers. So I've just clicked back on slide number 35. Just want us to utilize the formula there. Then we'll go back to our question. So we are checking that formula, n multiplied by p multiplied by 1 minus p. Our n is 200, our p is 0.4. Okay, so round 48. Audio is gone. Uh-oh. Okay, there's a comment that the audio is not there for some of our friends, but I'm sure others can get me since I've got answers popping up in the chat. Okay, so our n multiplied by p multiplied by 1 minus p is 48, which is greater than 5. Therefore, we conclude that our proportion can be approximated by the normal distribution. So that means that to find the probability, we're going to use the Z table. So the proportions that have been given are the probability that our proportion will lie between 0.4 and 0.45. And we have already seen that we're going to use the normal distribution. So we have to standardize the values, the proportions that have been given. So let's find our Z value for 0.4 and Z value for 0.45. Let's find the Z value for 0.4 and the Z value for 0.5 using the formula on the screen on slide number 37. Okay, I'm waiting for the Z values. Okay, I'm waiting for the Z values. Okay. We're taking time. So maybe we'll just go through together. So the Z values for 0.4, we'll have 0.4 minus 0.4 divided by the standard deviation, which is 0.03464. So you divide by that, and we're going to find 0. And on the other side, we're going to find 1.44. So now let's look for that probability that Z is between 0 and 1.44. Z is between 0 and 1.44. The probability that Z is between 0 and 1.44, let's get to our table. Okay, what is the probability from the table that Z is between 0 and 1.44? Okay, so we have an answer 0.9251. So we're looking for the probability that Z is between 0 and 1.44. What are others getting? Zero. 0.5. Waiting for more answers. Zero 0.95. I don't have a correct answer so far. There is no correct answer so far.
You are
0.67.
0.4251.
Okay, so that's the answer that I was looking for. How do we get that? How did you get that?
I went on the zero value, and the zero value is 0.5000. That's the first value there.
Yes.
Then I subtracted that from the value that I found from the 1.44 on the Z value is 0.9. Yes, 0.9251. Subtract that from 1. And the value you find is 0.0749. Then I subtract that value from the 0.5000, and then you'll get 0.425.
Why did you subtract 0.9251 from 1?
Sorry?
Why did you subtract 0.9251 from 1?
Because I'm taking it as a whole. Because each half is 0.5.
So you're saying that if you subtract that from 1,
yes, if I subtract the 0.925 from 1, I'll get the 0.0749.
Then what do you do?
Then I subtract that from the z value of the 0. Of 0, which is 0.5000.
So you actually get a negative answer. Oh, okay, I get it.
Yeah.
Okay. Okay. So okay, that was kind of okay. It's okay since you understand your method. Okay. So, but the simpler way to do this is just to go to the probability that Z is less than 1.44 is 0.9251. Okay, and the probability that Z is less than 0 is 0.5. So you just get your 0.9521 and subtract a 0.5. And you get the difference, which is a 0.4521. So 0.4521 is the correct answer. So you guys, you really need to practice how to read the tape. Because you can standardize, but then others were, even in the mid assignment, others were leaving the answer at this stage where you need to find the probability on the tape. So you need to know how to read the probabilities. Okay, so now we are moving to the next slide, which shows us that answer 0.54251. Okay, then the final part is finding sampling distribution of sample variances. Now, sometimes even on when we first introduced the sample means, we saw that we had different terms. So we can as well find variances for each sample, and we'll find that they will be different. So the times when we are concerned where if the sample variances are the same, or from the different sample variances, would want to find the mean of the sample variances and the standard deviation of the sample variances, and even the variance of the sample variances. So for the sample variance, okay, that's just how to find the sample variance. The mean of the sample variance is equal to the population variance. And that is how we obtain the variance if the population is normal. Now, if the population is normal, we say that the sample variances follow the chi-square distribution. So whenever we're finding probabilities of the sample variance, we use the chi-square distribution. Okay, so we use the chi-square distribution. So the chi-square distribution is just a family of distributions depending on degrees of freedom. So remember that from the t-distribution we had degrees of freedom. So even in chi-square distribution we have degrees of freedom, which is obtained by subtracting 1 from the sample size. Okay, so that just shows us. If n is 3, then the degrees of freedom is 2. If n is 8, then the degrees of freedom is 7. If n is 10, then the degrees of freedom will be 9. Okay, so we'll move to the next slide, slide number 46. We have an example. Now, in this example, we were taught, okay, let me just read the example. A commercial freezer must hold a selected temperature with little variation. Specification call for a standard deviation of no more than 4 degrees. A sample of 14 freezers is to be tested. What is the upper limit for the sample variance? What is the upper limit for the sample variance such that the probability exceeding this limit, given that the population standard deviation is 4, is less than 0.05. So in this example, we are given the probability. So we are just asked to find the sample variance. But we have also been given the population variance, which is population variance is 16, and and the population standard deviation is 4. We've also been given our n, which is 14. So we just use the formula for the chi-square. So the formula says n minus 1 a squared over sigma squared should give us the chi-square value. So we go on our table, the chi-square table, at 13 degrees of freedom and alpha, which is 0.05. What is our chi-square value? Okay, so let's go to our table. Okay, so we have our chi-square. Just make it smaller. So we want Okay. So we are looking for our chi-square value at 13 degrees of freedom, which is that row, and our alpha should be 0.05, so it's a bit smaller. So our alpha at 0.05, this is the fourth column from the right. So since so the fourth column from the right, we have at 13 degrees of freedom, we have 1, 2, 3, 4. So this is the value, 22.362. This is our chi-square value. Remember, we're given the probability and the degrees of freedom. Okay, that is how we have found our chi-square value. In many cases, you'll be given the degrees of freedom and the chi-square value, and then you need to find the probability. Okay, so in this case, we have our chi-square value, which is 22.36. Since we have that, then we can just go back to our formula. We can go back to our formula. Okay, so that is the value, 22.36. Okay. We can now go back to our formula. And since we know that this value is supposed to be equal to 22.36, we can cross multiply and solve for the sample variance. Okay. Now, another good example is the question from the mid assignment. Maybe let's just share that screen again. Okay, someone is. Okay, so let's check the question. Question 1C from the mid. Okay, so that's our second example. This is on question 1C. It says monthly rates of return on the shares of a particular common stock traded on the Lusaka Stock Exchange. Okay. Monthly rates of return on the shares of a particular common stock traded on the Lusaka Stock Exchange are independent of one another and normally distributed with a standard deviation of 1.6. If a sample of 12 months is taken, what is the probability that the sample standard deviation is less than 2.5? So in this case, following our formula for the chi-square, we have our n, which is 12, our standard deviation, which is the population standard deviation, is 1.6, and the sample standard deviation is 2.4. So we replace this in the formula and find the chi-square value. So what are we finding as our chi-square value? Remember, our standard deviation is 1.6, n is 12, and standard and our S is 2.5. Okay, so here from our example, we're just looking for this probability that that is less than 2.5. So let's replace N, and our S is 2.5 and our sigma is 1.6. What is the chi-square value that we are getting? N is 12. S is 2.5. And sigma is 1.6. Okay, this is our last example. So let's just, and actually this is where we're going to end. So let's just answer that question and I wrap it up after that. Let's find the chi-square value. Okay, let's find the chi-square value. No. The K was used in this formula when S was unknown. For us, K is known, so we don't need the K. We just need to, okay, maybe let me go to the previous one. Okay, so actually, I think the slide was misleading. Let's use this formula. Chi-square is equal to N minus 1 S squared over sigma squared. N minus 1 S squared over sigma squared. This is how we obtain the chi-square value. So we are using that formula. The chi-square value is equal to N minus 1 over S squared over sigma squared. Okay, so we are looking for the chi-square value obtained by using the formula N minus 1 multiplied by S squared over sigma squared. N is 12, S is 2.5, and sigma is 1.6. Okay, so we have 26.86. Okay. Okay, so some people typing. Okay, so that is the correct answer, 26.86. So now that we have 26.86, we remember we're looking for the probability that our standard deviation is less than 26.86. Okay, so then we go to our table and look for 28.866 and look for the probability. Okay, so this is the first step. The next is now to go and look for the probability on the table. So let's go to our chi-square table. Okay, so we go to our chi-square table. Okay, so as we go on our chi-square table, we need to take note of our degrees of freedom. N is 12. So our degrees of freedom will be n minus 1, which is 11. So we go look for the 11 degrees of freedom, and we follow that row until we have our 26.8. So we go to 11. Okay. So at 11, when we follow that column, do we have 26.86? No, we don't. Actually, the last number is 26.7. 26.75. Okay. So our last value is 26.75. So that means 26.8 should be somewhere this side. So the probability for Z to be less than 26.8 is actually greater than the probability that the chi-square value is less than 26.76. But what is this probability for 26.7? We need to know it. And it is that it's here our alpha is 0.005. That means the probability is 1 minus 0.05, which is a 0.995. But let me just show you the solution again. Okay, so let me just show you the solution.
You are now unmuted.
Madam, so if the value overshoots, we pick the nearest last number, or what? What do we pick?
Okay, so let's see from that. Okay, still loading. Okay, then if it overshoots, then we just conclude that the probability of the value that we are looking for is greater than the probability of the last value in that row. Okay, so I just want to show you the solution. Okay, so those of us who have the solutions, okay. Okay, those of us who have the solutions, what I've just stated is that to find the probability that S is less than 2.5, we use the chi-square distribution. But it would have been... Okay, so let me end this slide and I try and upload it again.
You are now on mute.
Okay, so this shouldn't take much time now. Okay, so we just have about 5 more minutes before wind up. We just wanted to show you the solution. So from here, I think we're able to answer question 1 of the mid assignment. Okay, I don't know why it's taking this much time. But those of us that have, I think all of us have the mid assignment solution, so we are able to see the solution. But, so I've said that the probability that we are looking for, so the probability that the chi-square value at 11 degrees of freedom is less than 26.85 is actually greater than 1 minus 0.005, which is greater than 0.995. So that was supposed to be our answer. But for those that were just writing it is equal to 0.995, I was still accepting. But you just have to now understand the concept, what that means. Okay, so it just meant that we couldn't find the value on the table, but the probability of the value that we are looking for is greater than the last existing value, than the probability of the last value in that row. Okay, so it's taking quite some time to load, but I think we can download what I wanted to show you and we can go through. Okay, so end here, unless there are questions. Okay, so if you are able to answer this question 1 in the mid assignment, just know that you are able to answer question 1 of the exam, not question 1, but at least one question from an exam. So you just have to understand the concepts, because I will not ask the questions, the exact questions, but it will be something similar. So if you can answer that question, then you're well and good. Okay, so we'll end here unless there are any questions.
You are now unmuted.
Madam, can we go back to the last example we had about the 0.4 and the 0.45?
Okay.
Okay.
Do you know the slide number?
Do you know the slide number?
No.
Okay.
Okay.
Okay, there it is. You want the question or the solution? Okay, so there it is. What's the question?
Okay, there it is.
Okay. So in your explanation, you said that because the method that I use is different, and then you said that the easier way we can do it is by multiplying the z value by 0.5.
The easier way that I provided was for the other question that had minus 0.4. And okay, I remember. I remember when you said that you subtracted from 0.1. Okay. Okay, so from this graph, you can see a 0 and a 1.44, right?
And the 1.44, right?
Yes.
So the probability to
So
the
the
left of
probability to the left of
1.44 was 0.9251.
0.9251.
Okay.
Yes.
Okay.
So this is the probability that scatters everything, even this, even the one that is not shaded. Just to the left of 1.11.
Okay.
Just to the left of 1.11. Yes.
So since we have the probability to the left of 1,1 and
This
everything,
probability to the left of 1,1
and
and
we just want
everything,
this shaded region, we can just subtract now 0.5, which is
we can
this
just
area,
subtract now
which is not shaded,
0.5
from the answer that we have.
area. This is not shaded.
Okay.
So we get
So we get
0.9521.
0.9521.
Okay.
Okay.
We get 0.9251 and subtracted 0.5, which is this area,
which is this area,
which we don't want, or which is
we
to the
don't
left of
want,
0.
which is to the left of 0.
All right.
And that gives us the
And that
shaded
gives
region.
us the shaded region.
Yes, understood.
Okay.
Okay.
Any other questions?
Any other questions?
Okay, we'll have our next lecture next week on Wednesday, and we'll be talking about confidence intervals. So let's study both confidence intervals for single proportions and multiple proportions. We'll try and do that in one lecture next week. Yeah, so that we move quickly. The exam is around the corner. So I wish you the best, and you can go through this and revise the mid since you have the solutions as well. Okay, thank you so much.
Thank
You
you.
are now unmuted.
Thank you, madam. Good evening.
Okay, thank you. Good evening.
Okay,
Thank you, madam. Have a good evening.
Thank you.